Well, in our previous lesson, we investigated springs that were connected in parallel, and you were given an equation that says the effective K value for any springs connected in parallel is nothing more than the sum of two springs' individual stiffnesses, or K values. So in this lesson, we want to talk about springs that are connected in series, as in this picture on the left. And I want to convince you that in that case, it's a different equation we need to use to find the effective K value. In fact, we find that the effective K value for springs connected in series can be found according to this reciprocal equation. The inverse of the effective K value is the sum of the inverses of the individual K values for the two springs that are connected in series. Now, I hope that you don't see these as the same two equations as each other. If so, I kind of say in jest, then I'd like to share a pizza with you. In fact, if I share my pizza with you, I'll be really generous, okay? Not only will I give you the half of a pizza that you're expecting, but I'll be so nice that I'll throw in on top of the half of a pizza, I'll also give you a third of the pizza. And so by being so nice, I will have given you 1/5 of the pizza. Clearly, math doesn't work that way, so these are definitely two different equations, right? Actually, this first equation tells us that the effective K value for any two springs connected in parallel is guaranteed to be greater than the largest individual spring. And this equation we'll find actually is a way of saying that the effective K value when you put the two springs end to end in series like this is actually less than the smallest spring's individual K value. But we'll add some numbers to this after we derive the equation. So the concept here is that the springs have to have the same force as each other. For springs in parallel, we said that the two springs share the exact same amount of stretch. Not the case here, but they would have to have the exact same amount of force. After all, there's a force vector downward, gravity, acting on this block, and so the upward force has to be of the same magnitude if it's in equilibrium, but that amount of force is transmitted down the line through each of the springs equally. So let's say we just took the top spring, just K number 1, and were to hang some mass from it. Then under a load of mg, spring number 1 would stretch some delta x number 1. And we could draw a diagram for number 2, but I'm more interested in what if we take spring number 1 and then from the bottom of it suspend spring number 2, then the amount of stretch is going to be greater. Both spring number 1 and spring number 2 stretch some amount as they share the common force that goes through both of them. And so the overall delta x value, I guess these should all be a delta x, huh? It's not so much the length of the spring that we're worried about in Hooke's law as it is the change in length of the spring. So the concept here is the same. What if I could find a single spring that originally is this long, so to match the two of them connected end to end. And then I hang this weight, mg, from that one spring, so it stretches and becomes this long. Then I've found a spring with an effective K value that matches the combination of the two springs in series. So delta x1 plus delta x2 is the same thing as delta x effective. Let's write that down. The effective change in length of the single spring is equal to the sum of the increase in length for spring 1 plus the increase in length for spring number 2. But according to Hooke's law, if indeed force is equal to K value times delta x, then I guess that means delta x is equal to F over K. So we have a force of mg divided by K effective. That would be a good substitute for delta x effective. That has to equal mg over K1 plus mg over K2. So in this case, we can cancel out all the mg, and we got the equation that I suggested earlier. the inverse of the effective K value is equal to 1 over K1 plus 1 over K2. And if you had 3, 4, 5, 6, 7 springs all connected together, then we could just carry on that equation. But we'll limit our study to just a combination of 2 springs. So if we want to put this formula into maybe a different expression that's a little easier to relate to, we could find a common denominator. And so we can say 1 over K, let's call it Ks instead of K effective, because now we're trying to find the effective K value for springs in series. So 1 over Ks would be equal to K2 over the product K1, K2, right? Plus K1 over the product K1, K2. So I can just add them together now that I have a common denominator and say this is K1 plus K2 over the product K1 multiplied by K2. But of course that doesn't give us the value of the effective spring stiffness. That gives us the inverse of the effective spring stiffness. So if we take the reciprocal of both sides of the equation, we get the effective K value for springs in series is equal to the product of the K values divided by the sum of the K values. Of course, that's right dimensionally, isn't it? If K value is measured in newtons per meter, then we have newtons per meter multiplied by newtons per meter, right? K1 times K2 divided by, well, when I add any two K values together, I just get some number of newtons per meter. And so this seems to be correct dimensionally. So let's take the example problem we had previously. What if K1 is 50 newtons per meter and K2 is 200 newtons per meter? The effect of this is that the two springs, when connected end to end, stretch even more under the load of the weight than the smaller of the two springs by itself would stretch. So in other words, we can multiply 50 times 200 and divide it by 250, and we'd end up with a value of 40 newtons per meter. So indeed, this is right. The effective K value for springs in series is always less than the K value of the smaller of the two, whereas the effective K value for springs that are in parallel is always greater than the single K value of the larger of the two springs. So it's a good exercise for you to try this. What if K1 is equal to 1 newton per meter and K2 is equal to 1,000 newtons per meter? Then I'd like you to do this exercise on your own. What would be the effective K value if those two springs were connected in parallel? And what would be the effective K value if those two springs were connected in series? I'll leave you on your own to see what you find out.